Okay, so let's solve this question. The question states that a regular language L is accepted by a non-deterministic finite automaton, that is a NFA. Okay, so this language L is accepted by NFA with n states, right? This NFA has n states. Okay, which one of the following statements is R false? So is R basically means that this is a MSQ question, multiple select type question. It would not have a negative marking, so we must attempt it. Second of all, it multiple choices can be selected, that is one thing, and it is basically asking us for the false statement, right? Truth and false statements, go for the truth values of statements. Do not really try to remember what is true or what is false. Just remember, write the truth value of the statements and then tally up the results at the end of the analysis that you have done of the statements, right? So do it that way. Now for the statements, let's read them and try to understand what they are saying. L may have an accepting NFA with less than n states, right? This NFA DFA that I'm expecting that you must know what is NFA DFA, and you have basically gone through some kind of material on theory of computation, but I will give a small reminder of what they are so that you can have a revision, small revision while you watch this. So basically NFA is basically your finite automaton like this, right, in which for every single state, right, this is the alphabet, a comma b is the alphabet. So for every single state, for one alphabet, there could be multiple transitions that are possible, and because multiple transitions are possible for every single state, you do not have a deterministic next state. That is why it's called NFA. And then there is DFA, in which this transition would be invalid, right? That is DFA. And then DFA can be then you have the concept of minimized DFA, right? The DFA with minimum number of states, right? Minimum number of the DFA which is having minimum number of states is basically unique, and that is a fundamental concept of this computer science. Now all three of them have the exact same power. That is, if you were to write a set of all the languages which are regular, right? These are regular languages. These are regular languages. So if you were to write a set of all regular languages, then every single one of these machines is going to accept every single language present over here, and any language which is not present in this set is not going to be accepted by any one of them. So they have exactly the same power. Basic revision of the subject. I hope that this serves some kind of positive reminder to or revision to you. Now let's get back to the statement. It states that L may have an accepting NFA with less than n states, right? So this statement can be understood by basically it's understanding based concept, because in NFA and DFAs also we always discuss about redundant states, right? States which are not needed and are adding no value to the language that is being produced. No, not produced, not accepted, because it is a machine, right? So a kind of state which adds no value to the accepting power of a machine is basically a redundant state, and both NFA and your DFA can have them. I will give you an example of that. So example of that would be this, right? This is a NFA because this A is basically being used over here to produce this transition, and at the same time produce this transition for this particular state. Hence it is a NFA, quite evidently visible over here. Now, and it is a NFA that is producing a kind of language which is basically represented by your A plus B whole clean star dot A. This is basically a regular expression which says that any kind of string which ends with a single A is basically accepted. That is the whole of this language, right? Now if I were to introduce, I hope that you would be able to understand what this is and how, because for if A and any A and B are possible, and after that if a single A comes, then we come to a end state, and if B comes, we go to the primary state one more time. If you were to introduce a second state like this one over here, then what? Any B comes, then we come over here. If A comes, then we come here. If B comes, we basically stay over here. Man, that is not really adding any kind of value, right? Because for B only we were staying over here, and for A we were going here, for A we are going here, otherwise we are staying here. What difference does it make? It does not really make any difference now, so it is not adding any value. So this over here is a redundant state, right? So, and now because the redundant state concept has been reintroduced into your mind, you must be able to think that the NFA over here has not been mentioned to not have any redundant states, right? So for having the possibility of having redundant state possessing n and totaling to n states, there could exist a n naught number of states which does not have any redundant state and is less than n, for which an NFA can be drawn, right? And that is what this statement coincides with, because it is saying maybe, because this NFA may have redundant states, may not have redundant states. So we are saying that if it may have, then we can construct an NFA which is not having redundant states, and that is going to have less than n states. So the truth value for this statement is true, right? Now the second statement says that L may have an accepting DFA with less than n states, right? L may have a accepting DFA with less than n states. Yeah, that is also possible. Yeah, that is also possible, because let's say that your NFA has extremely humongous amounts of redundant states, right? Just imagine in your head, right? And even after conversion from NFA to a DFA, the number of redundant states, because redundant states could be anything, could have enormous amount of redundant states, right? And DFA could be minimized, right? Both of these are possible. With both of these being possible, the number of states that the minimized DFA is going to have is going to be less than the number of states that the redundant, enormously redundant NFA would have. So this statement is true because it is stating maybe. I'm hoping that you're following along, because it is very clear actually what is actually happening. So this is also a true statement. Now third one is, there exists a DFA with less than equal to 2 raised to the power of n states that accepts L. Okay, so this is basically a kind of basic funda of theory of computer science. I will prove that there would exist a DFA of this sort, right? Prove, or more like, this is a kind of property that a DFA can be constructed from a NFA, given any NFA, no matter how redundant. A DFA can be constructed which is going to have states less than equal to 2 raised to the power of n being the states that are present in your NFA, right? This is a property in TOC, and I will prove it at the end of the video. Let that be stated. And this statement, by that proof that I will give, is basically a true statement, right? So this is a true statement. Okay, now the fourth one states that every DFA that accepts L has to have greater than 2 raised to the power of n states, right? So this is a false statement, because obviously this is true, so this has to be false. Obviously, because one more way in which you can see without even invoking this one is that a DFA could exist with less than n states, right? So this claim that every DFA has to have states greater than 2 raised to the power of n is absurd, right? So this is false statement, right? The truth value for this is false. Now once you have written all the truth values and the false values over here like this in a systematic manner, then basically revisit over here and just check, is it truth, are they asking for the true values or the false values? Because many of times the blunder that student commits in the examination is basically they solve the question correctly, but they get to a result and then basically remember that it was false when it was actually true, or it was true when it was actually false. So don't commit that blunder. Go and recheck this. The question paper is available to you all throughout the examination. There is nothing wrong in rechecking this one single word. And because you're looking for the false statement, you must mark the last option. And I know this is a MSQ type question, but over here only single option has to be marked, and that is the correct one, right? Now, as I promised you, the proof for this property that I talked about, I will just give you that. Basically, this proof comes from the method that we use to convert a NFA to a DFA, right? The method that we use to convert an NFA to a DFA is where this kind of property, this method is basically giving you this property, right? I will show you that. For that, I will basically do a conversion. This is an NFA, right? This NFA is basically representing a language that, if represented in regular expression terms, is basically equals to this thing, right? This is the language that they are expressing with this kind of NFA. Now, basically the strings that are going to be accepted for the language are basically starting and ending with A. That is the only requirement, right? If you were to convert this NFA, this NFA were to be converted to a DFA, what is the method? The method for this is basically you draw a kind of state table, right, with a starting state over here like this, and these are the states for the alphabet. These are coming from the alphabet being equal to your A comma B. Now, because it is a DF, it was a NFA, so deterministic aspect was not present, right? Deterministic aspect was not present, but now we're converting it into a DFA. So deterministic aspect must be introduced. And what is deterministic aspect? For every single member of your alphabet, for every single state, a single different transition must exist, right? For a single alphabet and a single state being present, right over here for A, only one kind of transition can occur. Right over here with A, there are two transitions, but only one must exist if it is a DFA. That is the kind of restriction that we have to impose. So let's draw with that, go on with that. With Q0, with A, you get to Q1. Very simple, not a problem. Now with Q0 at B, you don't go to anywhere because that is not even defined, right? Remember, mind you, that NFA does not have the concept of your dead state, right? Because dead state are basically ignored, directly ignored in your NFA, because it is non-deterministic. You do not need to tell it. Deterministic aspect forces you to define a dead state. There is no other use for dead state, right? So dead state is not present. Dead state, mind you, is this thing, basically a state from which there is no return, right? So if I were to do this over here, that is a dead state introduction, right? If a B transition were to be made over here, and after that, this is not an end state, so the string would not be accepted, and from over here any A and B combination is basically played out and the state remains unchanged, right? So that is what we call a dead state. Okay, so dead state basically over here we will represent by phi, right? Basically we got to a dead state because B was not defined. Very good. Now if we get to where Q, now do not look at over here like these states are present. We do not need to go from here. The states that we encounter while drawing from the starting symbol, right, from a starting state, once we go along like this, the states that we encounter are the only valid states, right? We do not consider these states directly anymore when we're converting, right? So with Q0 we got to Q1, and then from Q1, because Q1 was present over here, that is why we are taking it. Phi is not basically a state, so we will not take it, but Q1 is a state. I'm not taking it because it is present in our original NFA. I'm taking it because we got to that while drawing the state table. From Q1, if I were to get an A, then I will go where? I will go to Q1 and I will go to Q2. Both of them possible. Q1 A if I get, I will go here. If Q1 A I get, I will go here, right? So basically Q1 and Q2 both are possible. So I will write both of them, and that is going to constitute my new state, right? That is what I am going to do, Q1, Q2, right? And if I were to get a B over here, then where will I go? I will go to Q1 again. Right now, did I got a new state over here? Yes, I got a new state, and that is basically Q1 Q2, and I'm going to write it over here also, Q1 Q2, right? From this Q1 Q2, right, mind you, this Q2 was in the original NFA a end state, so this Q1 Q2 is also a end state, right? Now from this Q1 Q2, if I were to introduce an A, so I will look for both A's result, the transitions that Q1 makes on A and transitions that Q2 makes on A, and then basically accumulate them and write it over here, right? That is how we basically do the conversion from NFA to EFA. This is kind of a standard procedure, more or less, right? So from over here, if I were to get an A again, so I get, if from at Q1, if I were to get an A, I go to Q1 and Q2 one more time. Okay, so let's do that. So I get Q1 Q2 one more time, and from Q2 that is present over here, if I get an A, I don't make any transitions, so basically I stay over here. Fine. If I for B, if I were to define for over here, what do I get? From Q2, if I were to define a B, nothing happens. If I were to make a transition with Q1 with B, it goes to Q1 again. So this is Q1. So was any new kind of state introduced over here? No. So this is basically complete. This the whole state table for the DFA that we were constructing from the NFA is complete, and with this state table, basically this state transition table that we have, we can directly draw a DFA. That is very straightforward. This is basically your Q1 Q0. From over here, if A were to be present, you would go to Q1. Okay, with that you go to Q1, right? If you were to be given a B then at Q0, then you go to a dead state because it is a phi, right? So this is A comma B, this is a dead state, right? I'm not even naming it because it does not need to have a name, because does not have an entry in your state transition diagram. Now with Q1, if I were to get an A, I go to this Q1 Q2 state, Q1 Q2 state, right? And this is a dead state, this is the end state. Now if I were to get an A over here, I go here. If I get a B, then I stay at this state only. Okay, in this state, if I were to get an A, I remain over here like this. If I get a B, I go to Q1. And this is a DFA that corresponds to this NFA. Why did I do all this transition from a NFA to a DFA? Because the devil lies in the details of this method, right? Because every single state of the DFA can be a collection of the states of the original NFA, right? These states, when I collected Q1 and Q2 together, I got to the third state. No, this third state is only being generated because of a collection of these two states, right? That was just when you went along with this method, you got to this kind of thing, right? And because that is allowed, right? So the whole of the process can be viewed from a permutation combination point of view, and that is where the trick lies, right? If I were to look at this NFA, this has 3 states, right? And if I were to pick 0 number of states from that in a combination sort of way, right? This has 3, right? So n is basically equal to 3, which is equals to n, right? NC0, not picking any one of these states, is basically equal to your phi, and that is your dead state, right? So this corresponds to your dead state phi, plus 3C1. This corresponds to your Q1 possibility, Q0 possibility, Q1 possibility, and Q2 was not used, I know, but it was a possibility, right? So this corresponds to that, your Q0, Q1, Q2 possibility, plus 3C2. This corresponded to your possibility of it being Q0, Q1, Q0, Q2, Q1, Q2. Right, this is the possibility that we are considering, right? This kind of combination is basically representing, right? And every single one of them is a valid state of the DFA if it would have come in the process that we had followed, right? It is a valid state, right? We did not got it, that is a different story, but it is a valid state that we could have gotten, right? I'm going to reduce its size so that it is much more easily visible, right? You have software, why not use it when you have it, right? And this last one, the combinations completion, if I were to do 3C3, is going to represent basically your Q0, Q1, Q2. This is also a state that is possible but did not come up in this scenario, okay, but it is possible, right? So this, from a permutation combination point of view, this kind of sum is basically representing all of possible states that the DFA, the corresponding DFA, could have had, right? Right? Now let's replace this 3 with your n, and we as humans can perceive patterns, right? So I'm going to write this in a more formal manner, replacing 3 with n and then following all this till n, 0, 1, 2, 3, till n. What do I get? I got to the fact that total number of DFA states for n state NFA is basically equals to NC0, NC1, NC2 plus plus NCN, right? That is basically what are you coming with, right? There are no other possible DFA states that are possible that we can come up with while doing the conversion, right? So, and what is this sum equals to? This is basically binomial theorem, right? If you don't remember binomial theorem, it was very simple. Just look it on the net. I will write it over here so that you know what you have to search for. Binomial theorem. And basically from binomial theorem, I get 2 raised to the power of n. Right? This is what that thing is coming from. Right? This claim basically gives you that any DFA, if it were to be constructed, would have number of states less than or equal to 2 raised to the power of n, because there are no other possibility for arranging the original states of NFA. That is basically it's a very good proof that I've given. I know that some teachers may be able to express it in a better manner than I did, but this thing is the actual proof for why this thing exists, and this is what they are basically claiming when they are saying over here with the third statement. It is a true statement that there exists a DFA. There would obviously exist a DFA because every NFA has the same power as a DFA, so it can be converted into a DFA, right? And it, because conversion is completely possible and the method is defined and the method restricts us to this possibility of states that we can choose. So for every DFA, for every NFA, there exists a DFA that would have states less than or equal to crucial power of n states that will accept the same language, right? With that, I think that I've explained the whole question in a very good manner, and I do hope this added some kind of value to you. If you have any constructive criticism or every kind of positive input that you can give on how I can teach better, please to provide that in the comment section. And other than that, have a very good day. I will see you in the next video.